Hello again, it's Professor Bedrero, and we're ready to talk about inferences for two means. And today we're going to focus on when our samples are independent. Oops, sorry about that. And we're going to do our hypothesis testing and confidence intervals for two independent means. And we are taking two samples, and so we need to make sure that the data values from one data set are not linked to the data values in another set in any way, shape, or form. So first, dependent samples, we handle that using techniques from section 9.3. But as always, we need to start with a requirement check. So we want to make sure that our samples are independent. There's no link between the data values. In one data set, no link between the data values in the two sets. In the two samples. Okay. Also, as always, we need the samples to be random so that they are representative. And we need both samples to be normally distributed or greater than or equal to 30, so that we can use the central limit theorem and have a bell-shaped sampling distribution. Okay. All right. So let's do it through an example. I found out about this data from attending a conference, and there was an article published a little while back asking if SpongeBob SquarePants was bad for children. In fact, let me show you that. So here's the ABC News report on that from September 9th, 2011. Okay. So let's go ahead and analyze the data here. So they published an article in September 2011 in the journal Pediatrics. They took 40 children that were randomly and independently assigned to two groups. One group watched SpongeBob SquarePants, and the other group watched an educational video. And they were then given a test to measure their working memory, and they scored the children, and the highest score you could get was 60. We want to do a hypothesis test to see if the children who watched the SpongeBob video had a lower average score than the educational video, and we're going to assume a normally distributed data. So I'm going to pause the video here while I input the data into my calculator, and just because they gave them to me in this order, I'm going to put SpongeBob in list 1 and educational video in list 2. So go ahead and pause the video while you put that data in. Okay, we're back now that we've got our data in. Let's check to make sure that we can proceed by doing a requirement check. Did we have independent samples? Yep. The problem even told us that they were independent. Okay, meaning there's no relationship between this child and this child, this child and this child. There's no link between corresponding data values. Okay. Were the samples random? Yep. So they were randomly and independently divided there. Okay, we noticed that we only had 20 in each group, but if we make this assumption here that they're normally distributed, we can go ahead. Okay, so population 1, just because the order they gave it to me in, I'm going to have population 1 be the average working memory score for children watching SpongeBob. Okay, and population 2 will be the average working score, or well, we're going to be measuring the working memory score for children watching the educational video. Okay. All right. So X1 bar, I'll let you pause and run your one variable stats on list 1 and list 2 so we can put these in and we'll then come back together. Okay, so I got an average of 19.7 for the population 1, the working memory score for children watching the SpongeBob video on 20 children with a standard deviation of 10.68. For population 2, the working memory score for the children watching the educational video, I got an average of 33.85 on 20 with a standard deviation from that sample of 20.71. Okay, so we now need to determine our hypotheses for the test. We want to see if the children who watched the SpongeBob video had a lower average score than the educational video. And since SpongeBob was group 1, we want to see if the average for all children watching SpongeBob would be lower than the average for all children watching the educational video. And since SpongeBob was group 1, we want to see if mu1 is less than mu2. So let's go ahead and we can do either mu1 equals mu2, or if you want to get really technical, mu1 greater than or equal to mu2. And since this is going to be looking at our alternate hypothesis, a less than is to the left on the number line, so we're going to check for a left tail test. And to be upfront, we're going to say we're going to have a 5% level of significance. And since the only standard deviations that we know were from the samples, we can't use the, whoops, that's supposed to be standard deviation there. We can't use the Z distribution, we have to use the T distribution. Okay. And with our T distribution, we have to know the degrees of freedom. Now there's a really complicated formula for finding that down here, but I'm just going to use my technology, and let me show you that right now. So with my data in list 1 and list 2, you can see those in there. Okay, I'm going to go to stats, tests. Okay, I'm going to do a 2-sample t-test. Okay, and I'm going to tell it, I don't have the summary statistics, I have the actual data values. So I'm going to tell it that the data values for sample 1 are in list 1, and for list 2, that's the sample 2 data. We're going to leave frequencies at 1. And what's the alternate hypothesis? Our alternate hypothesis is that mu1 is less than mu2. Now, there's several ways you can do this. We're going to go with the camp that says no on the pooling of the standard deviations. So we'll do no there, and then let's go ahead and hit calculate. And it will tell us that the number of degrees of freedom would be 28.44. Okay. And we can then use our wonderful t-table to find the critical value. So if we look at basically 28 degrees of freedom and a 5% level of significance on a left-tailed test, so 28 degrees of freedom and 5% level of significance on one left tail, you'll see that that is the one area tail. So that's 1.701, but since we're dealing with the left, we need this to be negative 1.701. So there's our critical value for what we will decide is reject H naught or not. Okay. To keep these videos short, let me pause here and then we'll pick up in the next video.